For thousands of years, we've looked up and asked, what are those lights? But for our ancestors, the answer wasn't just wonder, it was survival. Deep inside the Lascaux cave in France, painted 17,000 years ago, lies a cluster of dots. This is the Pleiades, the oldest star map known to man. To a hunter-gatherer, the sky was a calendar. When certain stars rose, the herds would move. When they set, the frost was coming. The moon was the world's first tally. We found eagle bones from 30,000 years ago with notches carved to track the lunar cycle. In ancient Mesopotamia, the Babylonians took it further. They didn't just watch the sky, they measured it. They were the first true cosmic bookkeepers. On these clay tablets, they recorded the movements of Jupiter using complex geometry, 1400 years before Europeans discovered the method. To the ancients, the sun and moon weren't just rocks in space. They were gods. But gods that followed a very strict, mathematical schedule. Stonehenge. It's not just a pile of rocks. It's a 5,000-year-old astronomical computer built to predict the summer solstice with terrifying accuracy. The Great Pyramid of Giza is aligned to true north within 3/60ths of a degree. To do that, the Egyptians used the stars as their level. Every year, when the star Sirius rose just before the sun, the Egyptians knew the Nile was about to flood. The sky told them when to eat. Imagine your life depended on a single dot of light appearing 8 light-years away. That was the reality for the ancient world. Halfway across the world, the Maya were obsessed with Venus. Their calendars were so precise, they were off by only 1 day every 6,000 years. They didn't just look at the sky. They calculated the future. But how did they do it without computers? Wait, they had computers. Meet the Antikythera mechanism. A 2,000-year-old Greek device that could predict the position of the planets. An analog computer from the past. The ancients proved that with just eyes, math, and time, you can master the universe. But soon, things would get even more complicated. Act 2 begins. Welcome to ancient Greece. While others saw gods in the stars, people here started seeing something else, geometry. Meet Eratosthenes. In 240 BC, he heard that in Syene, the sun shone directly down a well at noon on the solstice. No shadow was cast. But in Alexandria, at the exact same moment, a vertical stick did cast a shadow. Eratosthenes realized this meant the earth was curved. Using simple geometry, he calculated the earth's circumference. He was off by less than 2%. All with just a stick and a shadow. Fact. If you shrink the earth to the size of a marble, Eratosthenes just measured it using nothing but the shadow of a toothpick. Comparison. Then came Aristarchus. He looked at a half-moon and realized the sun, moon, and earth formed a perfect right-angle triangle. He figured out the sun was much larger than the earth. So he asked, why would the giant sun orbit our tiny little planet? Hypothesis. Aristarchus proposed the earth went around the sun. But his idea was too radical for his time, it would be ignored for 1,800 years. Instead, the world chose Ptolemy's model. Earth was the center, and the stars were fixed on giant, invisible crystal spheres. Theory. But the planets did something weird. They seemed to move backward. To fix this, Ptolemy added epicycles, circles within circles. The universe was becoming a beautiful but incredibly messy cosmic clockwork. It worked, but it was just too complicated. During the Islamic Golden Age, astronomers like al-Battani refined these measurements to levels of precision that would later stun Europe. They translated the Greek knowledge and added their own. Without them, the map of the stars would have been lost in the dark. The foundation was laid. The math was ready. But the universe was about to get much, much bigger than anyone imagined. Next, we leave the ancient world behind to meet the man who dared to move the earth. Act 2 starts now. To truly understand the stars, we must travel back to Mesopotamia. Here, the Babylonians didn't just look at the sky, they turned it into a giant spreadsheet. For centuries, priest astronomers watched the horizon every single night. They were the world's first data scientists, recording every flicker of light. Their obsession? Jupiter. The king of planets. They tracked its path through the zodiac with a precision that seems impossible for their time. In 2016, researchers discovered they used trapezoid geometry to calculate Jupiter's velocity. A math trick we thought was invented 1,400 years later. They gave us the base 60 system. That's why there are 60 seconds in a minute, 60 minutes in an hour, and 360 degrees in a circle. Fact. But their greatest achievement was the Saros cycle. They realized that every 18 years and 11 days, the sun and moon returned to the same position. This meant they could predict eclipses. To the people, it was magic. To the astronomers, it was just very, very good accounting. Fact. They were so precise that modern NASA data on ancient eclipses relies on their records. Not bad for people writing on mud, right? While Babylon counted the stars, Egypt used them to build the foundations of civilization. They linked the heavens to the earth. They noticed that when the star Sirius rose before the sun, the Nile would flood. It was their celestial alarm clock. Fact. In the jungles of Mesoamerica, the Maya were creating the most complex calendar systems ever known. Their focus? The planet Venus. Their Venus table tracked the planet's cycle with an error of only 2 hours in 500 years. Let that sink in. Fact. From mud to stone to bark, different cultures, same sky. They all found the same cosmic rhythms independently. This wasn't just religion, it was data. It was the first time humanity realized the universe followed laws. Laws we could solve. But as we got better at math, we started asking a dangerous question: what if we aren't at the center of all this? Chapter 4 awaits. To move forward, we must go to Alexandria. Here, the universe stopped being a myth and started becoming a puzzle that could be solved with a stick. The Egyptians mastered the Sothic cycle. They knew Sirius returned to the same spot every 365.25 days, the exact length of our year. Fact. Then came Aristarchus. While others just watched, he used the shadow of a half-moon to calculate the distance to the sun, history. He realized the sun was 20 times further and much larger than the earth. It was the first hint that we weren't the center of everything. Hypothesis. Ancient scholars even calculated the Earth's tilt, 23.5 degrees. Without this lean, we wouldn't have seasons, only a permanent, boring spring. Fact. Eratosthenes then performed the most famous stick and shadow trick in history to measure the entire planet's circumference. Fact. He was off by less than 2%. Over 2,000 years ago, we already knew Earth was a sphere, and we knew exactly how big it was. Fact. But then came Ptolemy. He gave us a model that would last for 1,400 years, the geocentric universe. Earth at the dead center. Theory. But there was a problem. Planets like Mars sometimes seem to move backward in the sky. This retrograde motion drove astronomers crazy. Fact. To fix it, Ptolemy invented epicycles, circles within circles. It was like trying to fix a broken watch by adding more broken parts. Theory. While Europe entered the Middle Ages, the Islamic Golden Age kept the light on. Astronomers like Al-Battani perfected the math. History. They translated, preserved, and improved ancient data. Without them, the Renaissance would have been a very dark place indeed. But in 1543, a Polish priest named Nicholas Copernicus decided to do the unthinkable. He kicked the Earth out of the center. Fact. The Earth was now just another planet. A spinning rock orbiting a giant star. The modern universe was born. Theory. But proving the Earth moved would take more than just a theory. It would take a man with a new kind of lens. Phase 5 is next. The year is 1609. In Venice, a man named Galileo Galilei hears of a Dutch toy that makes distant objects look closer. He decides to build his own. Galileo didn't just look at ships. He pointed his spyglass at the heavens. And what he saw would get him in a lot of trouble. The moon wasn't a perfect, smooth heavenly sphere. It had mountains, valleys, and craters. It was a world, just like Earth. Fact. In 1610, he found 4 stars orbiting Jupiter. These weren't stars, they were moons. Proof that not everything revolved around the Earth. Fact. Then came the killer blow: Venus had phases like the moon. This was physically impossible if the sun went around the Earth. Fact. Galileo published his findings, but the world wasn't ready. The Earth had to be the center, or the entire social order would collapse. He was tried for heresy, forced to take it all back. But as he left the courtroom, he reportedly whispered, "And yet, it moves." History. While Galileo fought the church, Johannes Kepler fought the math. He realized the planets didn't move in perfect circles, but in ellipses. Kepler's 3 laws finally explained how the planets moved. The celestial gears finally fit together. Fact. Kepler 1609–1619. But there was one giant question left: why? Why do they stay in orbit? Why don't they just fly away into the dark? Enter Isaac Newton. In 1665, while hiding from a plague, he saw an apple fall, and realized the force that pulled the apple was the same force that held the moon. Gravity. The invisible glue of the universe. Newton proved that the heavens and the Earth follow the exact same laws. Fact. Principia 1687. With Newton's math, the universe became a predictable machine. We could finally calculate where the planets would be 1,000 years from now. But as our telescopes got bigger, we realized the solar system was just a tiny part of a much larger, and much stranger, galaxy. The clockwork universe was perfect. But soon, a young clerk in a patent office would come along and break time itself. Phase 6 is next. For Newton, time was like an arrow, straight and unchanging. But in 1905, a patent clerk named Albert Einstein realized time is a river that can slow down or speed up. Einstein's special relativity proved that the faster you move through space, the slower you move through time. Space and time are one, spacetime. Fact. 10 years later, he showed that gravity isn't a mysterious force, it's the curvature of spacetime itself. Imagine the sun sitting on a cosmic trampoline. In 1919, during a solar eclipse, Arthur Eddington proved Einstein was right. He saw starlight bending around the sun. Gravity was geometry. Fact. By 1929, Edwin Hubble discovered something even more shocking. The galaxies aren't just sitting there, they are all rushing away from us. Think of the universe like a balloon. As it inflates, every point moves away from every other point. The space itself is growing. Theory. Hubble saw this through redshift. Light from distant galaxies stretches out, turning redder as they move away at incredible speeds. Fact. If the universe is expanding today, it must have been smaller yesterday. A priest named Georges Lemaitre proposed it all started from a single point. The Big Bang. Not an explosion in space, but the sudden expansion of space itself. 13.8 billion years ago, everything was here. Theory. In 1964, two radio astronomers accidentally heard the echo of that explosion. A constant static hiss coming from every direction in the sky. Fact. Even today, 1% of the snow on an old analog TV is actually the cosmic microwave background, the oldest light in the universe. This map is the baby picture of our universe. The tiny temperature ripples here would eventually grow into the galaxies we see today. Fact. But in 1998, we found a mystery. The expansion is accelerating. Something called dark energy is pushing the universe apart. Theory. If this continues, the universe will become cold, dark, and empty. This is the heat death, the final chapter of everything. Speculation. The universe is bigger and stranger than Einstein ever dreamed. But what's hiding in the parts we can't see? Dark matter is next. Everything we have seen so far, stars, planets, and you, only makes up 5% of the universe. The rest is a ghost. Fact. In the 1970s, Vera Rubin noticed something impossible. Stars at the edge of galaxies were moving just as fast as stars near the center. History. By all laws of physics, these galaxies should be flying apart. They don't have enough visible mass to hold on to their stars. There must be something invisible providing extra gravity. An invisible glue we now call dark matter. Theory. Dark matter forms a massive web across the cosmos. It's the scaffolding that allowed galaxies to grow in the first place. Fact. It doesn't reflect, emit, or absorb light. It passes right through you and me like we aren't even here. Fact. In the bullet cluster, we saw it in action. The gas, pink, crashed, but the dark matter, blue, sailed right on through. Fact, NASA/Chandra. Is it a new particle called a WIMP? Or tiny black holes from the Big Bang? We have many ideas, but zero proof. Hypothesis. Now, the James Webb Space Telescope is finding galaxies in the early universe that are far too big, far too fast. Fact, JWST 2023. It's like finding a fully grown adult in a nursery. These impossible galaxies might mean our theories on dark matter are wrong. Hypothesis. If we can't find dark matter, maybe we don't understand gravity at all. Some propose modified Newtonian dynamics. Hypothesis. But while dark matter pulls things together, something else is pushing the entire universe apart. Meet dark energy. Fact. The recipe for our universe is weird: 68% dark energy, 27% dark matter, and only 5% of the stuff we actually know. Fact. We are living in a dark universe, built on things we can't touch or see. It's the ultimate cosmic mystery. We've mapped the ghosts of space. But what about the monsters? The kings of darkness are coming. Black holes are next. For a century, they were considered a mathematical mistake. A place where gravity is so strong that even light, the fastest thing in the universe, cannot escape. In 1916, while fighting in World War I, Karl Schwarzschild solved Einstein's equations. He found a point of no return, the event horizon. History. If you crushed our sun down to the size of a small town, just 3 kilometers wide, it would become a black hole. Fact. At the heart of almost every galaxy lies a monster. A supermassive black hole, millions or even billions of times heavier than the sun. Fact. Time behaves strangely here. If I watched you fall in, your clock would slow down until you seemed to freeze at the edge forever. Theory. But for you, the journey would be uncomfortable. Gravity would pull on your feet harder than your head. We call it spaghettification. Theory. In the 1960s, Roger Penrose proved that Ho-Den aren't just possible, they are inevitable once a star collapses. Fact, Nobel 2020. Then Stephen Hawking showed that black holes aren't completely black. They slowly leak energy, Hawking radiation, and eventually evaporate. Theory. To finally see one, we turned the entire Earth into a single telescope. In 2019, we captured the first image of a Ho-Den in galaxy M87. Fact. It looked exactly like the math predicted. A shadow of nothingness, surrounded by the light of screaming gas. Fact, EHT 2019. 3 years later, we saw our own Sagittarius A star. The quiet giant at the center of our Milky Way. Fact, EHT 2022. But these are tiny compared to TON 618. It's 66 billion times heavier than the Sun. It doesn't just sit in a galaxy, it is the galaxy's master. Fact. Black holes present a paradox. If information goes in and the Ho-Den evaporates, does the information disappear? Physics says that's impossible. Theory. The holographic principle suggests the entire universe's data might be stored on the surface of black holes. Like a cosmic hard drive. Hypothesis. We have reached the edge of what we know. But what if we could go further? What if Ho-Den are doors to somewhere else? Wormholes are next. If black holes are the ultimate cosmic traps, where does all that matter go? Some scientists suggest they might be doors to another place. In 1935, Einstein and Nathan Rosen found a mathematical bridge connecting two distant points in spacetime. We call it a wormhole. Hypothesis. Theoretically, a wormhole could act as a shortcut, allowing you to travel light years in a single second. But there's a catch. Speculation. They are incredibly unstable. The moment you step in, gravity would slam the door shut. To keep it open, we need exotic matter with negative energy. And if Ho-Den swallow everything, some theorists imagine their opposite, white holes. Objects that nothing can enter, but only leave. Hypothesis. But as we look deeper into the math of the universe, some ask a more disturbing question. Is any of this actually real? The simulation hypothesis suggests that a highly advanced civilization might have built a computer powerful enough to run a whole universe. Hypothesis. If they did it once, they could do it a billion times. Statistically, that would mean we are much more likely to be the code, not the creators. Speculation. Think about the Planck length, the smallest possible scale. Below it, space becomes grainy. Is that the resolution limit of our cosmic software? Some look for bugs, glitches in the laws of physics. But so far, the simulation seems to be running a perfect, error-free program. Fact. And if this is just one program, what about the others? The multiverse hypothesis suggests we are just one bubble in an infinite sea of universes. Hypothesis. In some, the laws of physics might be different. Gravity might repel, or stars might be made of liquid. The possibilities are truly infinite. Speculation. But infinity leads to paradoxes. Like the Boltzmann brain, the idea that it's more likely for a brain to spontaneously form in space than a whole galaxy. Hypothesis. Wormholes, simulations, multiverses, we have moved far beyond what we can see. We are now exploring the very limits of logic itself. Our journey through time and space is almost over. But the most important discovery of all might be happening right now. The final chapter is next. We are children of the light. We live in a brief, brilliant moment called the Stelliferous Era, the age of stars. But it won't last forever. In 100 trillion years, the last star will flicker out. The universe will enter the era of degeneracy, where only cold rocks and black holes remain. Theory. White dwarfs will slowly cool down, eventually becoming black dwarfs, frozen spheres of diamond and iron, invisible in the dark. Hypothesis. It's a cosmic tragedy. No matter how much we try to save them, the fuel of the universe is finite. Entropy always wins. Even matter itself might not be stable. If protons decay, every atom in the universe will eventually dissolve into pure energy. Hypothesis. By the year 10 to the 100th, the last black holes will evaporate. A final flash of Hawking radiation, and then, nothing. Theory. This is the heat death. A universe at maximum entropy. No heat, no light, no information. Just a cold, eternal silence. Theory. But don't be sad. The fact that the universe has an end only makes our time in it more precious. We are the universe experiencing itself. As Carl Sagan once said, we are made of star stuff. We are a way for the cosmos to know itself. History/philosophy. Every discovery we've made, from the first cave paintings to the mirrors of the James Webb, is a step toward understanding our home. The universe is vast, cold, and often terrifying. But it is also beautiful, and we are the ones who get to witness its glory. So keep looking up. The story of the universe is still being written, and you are part of the script. Thank you for traveling with me. If you enjoyed this journey through time and space, don't forget to like and subscribe for more cosmic stories. See you in the next galaxy. Remember, you are not just in the universe is in you. Stay curious, explorers. Developed by Hathan. Specialist in YouTube. Visit hathanhyoutube.vn for more. Credits: NASA, ESA, Nature, Science.